Okay, this is a recording of the 1.5a worksheet solutions. Don't pay attention late. We started school a lot later this year. Let's start with just exercise 1 through 6. Determine whether the function has an inverse function. Remember, in order for a function to have an inverse, it must be a one-to-one function. And one-to-one functions means that the graph passes both the vertical and the horizontal line test. So this is a function. It passes the vertical line test, but it is not one-to-one because it does not pass the vertical line test. So no, it does not have an inverse. This has an inverse. It's an always increasing function. So one-to-one functions are always increasing or always decreasing. In this case, we have an always increasing function. So it has an inverse. We could switch x and y and resolve for y. This one is one-to-one. It passes both the vertical line test and the horizontal line test. So yes, it has an inverse. As a matter of fact, if you switch x and y and resolve for y, you get the exact same thing back out. That's why this is called the inverse function. The inverse function of 1 over x is 1 over x. And 4 does not. It is a function. It passes the vertical line test, but it does not pass the horizontal line test. Y equals 1 over x squared plus 1. Notice this x squared plus 1 gives you this bell-shaped curve. We're going to see this graph quite a bit in later chapters. Remembering that this does not have a vertical asymptote because x squared plus 1 can't ever equal 0. Matter of fact, if you plug 0 in, you get 1 out. So this is a graph that we're going to see a lot. It's this bell-shaped curve graph. Okay. What about 5? 5 is an always decreasing function. Therefore, we can find the inverse. We could switch x and y and resolve for y. We would get a cube root function. But 6 does not have an inverse function. It's the first time we see this integer of x. We're going to see it frequently in chapter 2. You should have graphed it at some point, probably in Honors Algebra 2 or Honors Pre-Calculus, where you get solid dots on the right, open circles, or solid dots on the left, open circles on the right, and it jumps up. It does not pass the horizontal line test. If you draw a horizontal line through any integer value, it cuts the graph in more than one place. It is a function. It does pass the vertical line test. Every x coordinate has only one y coordinate because we have solid dots on the left and open on the right. But this is a function we're going to see again. We'll talk about it in more detail when you graph it. But the integer function does not have an inverse. What about these? Without a graphing calculator, some of these would be tough to tell. This one here does have an inverse. You could switch x and y and resolve for y. It would take some work to resolve for y, but we could do it. 8. This is a parabola that opens upward. So it is not one-to-one. It does not have an inverse. 9. This is a cubic that turns. It grows and turns and then grows again. So it has a maximum and a minimum. It's kind of hard to tell that it has a max or a min without applying some calculus to it or without typing it in your graphing calculator. So you may have to look at this one in your calculator, but the answer is no. We cannot switch x and y and resolve for y. 10 is an interesting problem in that 10 does have an inverse. X cubed plus x is an always increasing function from left to right. Since it's always increasing, it has an inverse. But we really can't find it algebraically. If we switch x and y, we can't resolve for y because of this x cubed plus x scenario. Not without a lot of work, at least. But this, if you type it in your graphing calculator, you'll see it's an always increasing function. So it does have an inverse. It just may be difficult to find. 11 does not have an inverse because x is being squared. If that squared was not there, it would be yes. So the natural log of x does have an inverse function. The inverse of a natural log is an exponential. So 12 is yes. This is an exponential function. An exponential function is either always increasing or always decreasing. So this has an inverse. Again, you can type it in your calculator and see that it is 1-to-1. Problem number 14. Find the inverse, then check the composites to verify that your inverse is correct by showing that f of f negative 1 of x equals f negative 1 of f of x equals x. Let's start by finding the inverse. So I break it down into 3 components. To find the inverse, I replace f of x with y, and I switch x and y. X equals 5 minus 4y. Then I'm going to resolve this for y. If I add the 4y to this side and subtract the x over here, I get 4y equals 5 minus x. Divide both sides by 4, and we get y equals 5 minus x divided by 4. You could write this a number of different ways, but this is good enough. I've gotten y by itself. I'll just leave it like this. But now I have to check my composites. I have to show that f of f negative 1 of x equals x. So I have to take x, plug it into the inverse function. This comes out. Whatever the output is from the inverse function becomes my input into the f function. Remember, we already know the answer is going to be x. We're just verifying that indeed we do get x. So the process here is more important than the answer. We need to see the 5 minus x over 4 come in for x right here in the f function. You can see that written, 5 minus 4 times the input. I can cancel these 4s. They're both factors. And then I can distribute the negative sign to both terms in the binomial that's left. Remember, never cancel factors and terms in the same step. That's how we separate how this is being processed, by canceling the factors separate from the terms. And we do indeed get x. Now we have to check the other composite. Take x, plug it into f. You get 5 minus 4x out. This now goes into our inverse function. The inverse function says take 5 minus whatever comes in and then divide by 4. 5 minus this is coming in, and then divide that difference by 4. I have to distribute the negative sign, but notice in this case, the second to last step is canceling the 5s, and the last step is canceling the 4s. That's why I can always tell if you process this correctly by looking at the last 2 steps, because they're usually different, and we get x. Okay? Remember, we're going to write the summary statement each time. Since f of f negative 1 of x equals f negative 1 of f of x equals x, the functions are inverses. It's always the same statement. We're not writing it because it's difficult. They essentially tell you what you're supposed to be verifying, but we want to get used to writing. Since this is true, then this is true. We're going to have to justify much more than you would ever imagine on the AP test. There's several different times where you're going to reach a conclusion and it will say justify or explain. So we want to get used to writing these statements, and we're going to practice that right now in chapter 1. Okay? It gives you a little bit of time to write this down as well. Remember, you can always pause this recording if you need to get more detail written down. Problem number 16, we're doing the same thing. Notice that this is a quadratic. A quadratic is not a one-to-one function, so it does not have an inverse. However, if we limit that quadratic to a one-to-one portion, then we can find the inverse. So this is a parabola that opens upward. It starts at 0, 1, and it opens upward. So we just limit this function to the right-hand side. We eliminate the left-hand side by giving it this domain. Now we can find the inverse. We can find the inverse of this limited part of this function. doing the same that we've always had, the same steps. Write it in terms of y. Switch x and y. Resolve for y by subtracting 1, taking the square root. The key here is, do I want the positive square root or the negative square root? Sometimes you want the negative. But on this problem, it is the positive. Because if x is greater than or equal to 0 is my domain in the original function, then that should be the range in my inverse function. And the range means if the domain here is x is greater than or equal to 0, our range here has to be y is greater than or equal to 0. So we want positive values for y, not the negative values for y. Remember, if domain and range are switching roles, this function is only defined when x is greater than or equal to 1. Because this original function is only defined when y is greater than or equal to 1. That's the range. That's the y values we'll get out, greater than or equal to 1. So this is the inverse function, and we have to utilize the domain and range of the original function to establish which piece we want, the top or the bottom, and then to determine the domain of that inverse. I still have to crank out these composites. F of f negative 1 of x. Take x, plug it into the inverse function. This comes out. So we're really practicing composites here. And the nice part is we're practicing composites and we know the answer. We know the answer should be x if we found the inverse correctly. Now this comes into the original function. The original function says whatever comes in, square it and add 1. The square root of x minus 1 is the input. Square that and add 1. If I square a square root, it simply gets rid of the square root. And negative 1 plus 1 cancels to produce an x. So far, so good. Now we have to do the composite in the opposite order. F negative 1 of f of x. Take x. Plug it into the f function, x squared plus 1 comes out. X squared plus 1 is the new input into the inverse function. The inverse function says take whatever comes in. X squared plus 1 comes in. Subtract 1 from it. Okay? And then take the square root. There it is. The plus 1 and the minus 1 cancel. And the square root of x squared is indeed x. Since f of f negative 1 of x equals f negative 1 of f of x equals x, the functions are inverses. Right? That's a nice question because it deals with this domain restriction. It's very important that we realize there's a lot of functions that operate that way. Just think of the square root function and x squared. The square root function is the inverse function for x squared, but only when x is greater than or equal to 0, right? So domains make a difference when we're looking at these particular problems. Now, if the function is defined over the entire domain, then it's no problem. Let's take a look at 21 or 22. Okay, so for problem 22, write it using y instead of f of x, switch x and y. Now I have to resolve for y. Well, it's in the denominator. So I have to multiply both sides of this equation by y cubed. It will cancel on this side, and I'll get x times y cubed on the left side. There it is. Divide by x, because I'm trying to isolate y. Divide by x, we get this. Take the cube root. Well, the cube root of 1 is 1. 1 times 1 times 1 is 1. Over the cube root of x. That's my inverse function. 1 over the cube root of x. Let's crank out the composites. Take x, plug it into the inverse function. When you plug x into the inverse function, this comes out. 1 over the cube root of x comes out. There it is. But this is the new input into the f function right here for x. So it's 1 over whatever comes in cubed. 1 over the cube root of x cubed. That replaces that x right there. 1 cubed is 1. The cube root of x cubed is x because the cube undoes the cube root. 1 over x is x. This means take the reciprocal of 1 over x, which is x. Let's crank it out the other way. Take x, plug it into the f function. When you plug x in, you get 1 over x cubed. That's the new input into the inverse function that we found right here. So 1 over x cubed comes in for x. 1 over the cube root of 1 over x cubed. The cube root of the numerator, the cube root of 1, is 1. The cube root of x cubed is x. Notice the last step is the same in both of these. So when we flip, we still get x. It's the second to last step that's different. And that's what I'll look at carefully to make sure that you are actually cranking out the composites correctly, not just making something up and setting it equal to x, because we already know the answer. We're verifying. Remember, since f of f negative 1 of x equals f negative 1 of f of x equals x, the functions are inverses. It's the same statement every time. We're going to get used to stating it every time. We will do the same thing when we do justifications on the AP test. Next problem. I'll leave that there for a second for you to write it down. We have one last problem, but it's the hardest one. I did an example like this for you so you could see one. There's one in the notes, there's one here, and there's a good chance that there could be one on the test. I like these problems because of the algebra involved. If you can get through all of the algebra in this particular problem, both in finding the inverse and in justifying the compositions, then you're pretty good with fractions. This is where we need to be in terms of our fractional manipulation. Let's start with finding the inverse. Y equals x plus 3 over x minus 2. I just replace the f of x with y. Then I switch the x and the y variables. Wherever there's a y, I put an x. Wherever there's an x, I put a y. If I want to resolve for y, I can't do it right now. There's some on top, some on the bottom. I need to get everything on the same level. So I multiply both sides of this equation by y minus 2. If I multiply the right side by y minus 2, it just cancels with the denominator. If I take x times y minus 2, I get something that looks like this. For lack of anything better to do, let's distribute the x, because I have these parentheses that are creating problems. So I distribute the x. xy minus 2x equals y plus 3. Now I simply have an equation that involves 4 terms. 2 terms have the variable y that we're trying to isolate, and 2 terms do not have a y. So I'm going to add this 2x to the right-hand side, and I'm going to subtract the y to the left-hand side, so that I get every term involving y on one side of the equation, and all terms not involving y on the other side. Why do I do that? Because now that every term involves y on this left-hand side, I can factor y out front. When I factor out this greatest common factor, I'm left with x minus y. Remember, I'm just undistributing the y to get y times x minus y. And if I want to get y by itself, I'm going to divide both sides by an x minus 1. There it is. 2x plus 3 over x minus 1. That is my inverse function. Let's just see if it makes sense. The vertical asymptote in the original equation was x equals 2. That's the value of x that makes the denominator equal 0. That means the horizontal asymptote in the inverse function should be y equals 2. Well, there it is. Degree on top, same as degree on the bottom. Y equals 2 is the horizontal asymptote. The horizontal asymptote in the original equation was y equals 1. Degree on top is the same as the degree on the bottom. So look at the ratio of the coefficients of those highest degree terms. 1 over 1 is 1. That means the vertical asymptote in the inverse should be x equals 1. Well, look at that. I think it's good to always check your asymptotes to see if they switch roles before you start your compositions, right? Let's not crank out compositions that might be wrong. Let's make sure that the vertical asymptote in the original shows up as the horizontal asymptote in the inverse. And the horizontal asymptote in the original shows up as the vertical asymptote in the inverse. But now we need to crank out these composites. This is the last problem, but here it is. F of f negative 1 of x. Take x, plug it into the inverse function. This comes out. So 2x plus 3 over x minus 1 is the new input into the f machine. This defines the f machine. Whatever comes in, add 3, all over whatever comes in, minus 2. So this 2x plus 3 over x minus 1 is coming in right here and right here in the original function. There it is. Going from complex to non-complex. Listen, there's a bunch of students who have just done it this way since the very beginning that want to multiply this by x minus 1 over x minus 1, distribute, get this all to be one fraction. Multiply this by x minus 1 over x minus 1, distribute the negative 2, get this all to be one fraction. Have this big, complex, messy situation and multiply by the reciprocal and simplify it down. You can do that. You can do that. It's significantly more writing than the way that Mr. Hearn talked to you about last year, and which I would agree with completely. Why not just multiply the top of this big fraction right here? Multiply the whole top by x minus 1 and the whole bottom by x minus 1. That's algebraically legal. That means I have to multiply every term by x minus 1. If I multiply this first fractional term by x minus 1, the denominator just cancels, and I'm left with 2x plus 3. But I have to multiply this 3 by x minus 1 as well. If I multiply this fraction by x minus 1, the x minus 1's cancel. But I have to multiply the negative 2 by x minus 1. But complex to non-complex in one step. If this is giving you problems, come see me. This would be a good item for you to come and talk to me about, because you want to be able to go complex to non-complex in one step, not 2 or 3 steps. Because now I can simplify the numerator by distributing the denominator. Distribute, don't forget negative times negative is positive. Cancel terms that cancel. Collect like terms, we get 5x over 5, which cancels to be x. Just what we're supposed to get. We're supposed to get x. As if all this isn't bad enough, now we need to crank it in the opposite way. Take x, plug it into the original function. That's what comes out. X plus 3 over x minus 2. That's the output. That output becomes the new input into our newly formed inverse function. That means that x plus 3 over x minus 2 is coming in right here for this circled x and right here for this circled x. I can still do that same trick. What is the denominator of this numerator? X minus 2. What is the denominator of this? X minus 2. So I'm just going to multiply every term by x minus 2. If I multiply this term by x minus 2, the x minus 2's will cancel. And I'm left with the 2 times x plus 3. I also have to multiply this 3 by x minus 2. If I multiply this fraction by x minus 2, the x minus 2 will cancel. That's why I'm doing it. I'm left with an x plus 3. But I also have to multiply this negative 1 by x minus 2. Complex to non-complex in one step. Multiply 1, 2, 3, 4, all 4 terms by x minus 2. The x minus 2 will cancel in 2 of those terms, the first 2 terms on top and on bottom, but I have to multiply the constants by that factor as well. It's the same thing. You will end up with the same thing here by making this all one fraction, making this all one fraction, simplifying everything down and multiplying by the reciprocal. It's just a lot more work. Distribute the 2. Distribute the 3. I show that right here. Distribute the negative sign. So from here to here is nothing but distributions. Add like terms. 2 of the terms are going to cancel. The other 2 we can add together and get 5x. Here the x's cancel. 3 plus 2 is 5. Now that these are factors, I can cancel. Never cancel terms and factors in the same step. Cancel the 5s and we get an x. Don't forget to write the summary statement. Since f of f negative 1 of x equals f negative 1 of f of x equals x, the functions are inverses. Okay, and I told you the challenge problems will not be on the worksheet, but you are certainly more than welcome to try some of these challenge problems if you'd like. I can provide some solutions for you if you're interested, but these are decent things to look at. But being able to find an inverse and then crank out the composites to verify that the inverse is correct will be on the test. Okay, that is the end of this worksheet.